Okay, we have been answered the question until we continue from the question number 10. That is computer we have done already. Okay, so we continue on question number 11. Okay, question number 11 is it says a diagram shows that two parallel metal plates uh, JK and LM in the evacuated region. So LM is maintains positive potential difference, whereas relative to JK, electrons of relative V electrons enter the space between the plates as shown below. So in this question, it should be there's supposed to be a hole here, right here. Supposed to be the hole. The electron charge E is E, and electron the mass is M. The kinetic energy of electron that just reached the plate JK is which one? So okay, which plate is a positive plate? Uh, it depends on the electric field. Okay, electric field is the one who want to determine where is the positive or negative plate. So remember when we have this equation E equals to negative dV over dr. So we know that V is inversely to E. If V is positive, E is negative. Or if we have another way, because V is negative, E is positive. So it says that it's a positive, Lm is positive. So Lm is positive V. So it means that at this point, E is negative. So we know that Lm is negative E, so this one will be positive E. Place of Jk will be positive E. So that's why the electron is coming towards the Jk because it's positive E, where actually we have a positive, 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 positive on the top of it, and this one it will be negative. Okay. So there's a reason why it doesn't goes to Lm. It goes to Jk because the Jk is the one having the positive plates. Okay, and as we know, uh, it will be parallel. It will be the work will be perpendicular to the plate, so it will have to count on this side. This side. So actually, it will be half mv squared equals to EV, the work done, EV. So V is, we have to count from half m, where V equals to V cos theta, because theta is the one is perpendicular to the JK. Okay, so equals to EV. So this side V cos theta is really the straight line that going to the JK. Okay, so answer will be B over here. Okay, question number 12. The diagram shows a conducting ring coaxial with the permanent magnet. When the ring is dropped with the plane horizontal, at what location will instantaneous acceleration of the ring equal to the acceleration of the gravity? So this is a question. It's a phenomenon of eddy current and a phenomenon of Lenz's law. Two things occur in this situation. If we have a metal ring, this metal ring, when you drop a metal ring, as a metal ring does has a is a conductor. When a metal ring drop into magnet, the metal ring will be slowing down because the magnet will induce a current. There will be current induced inside the metal ring. So when you drop the metal ring inside the on the met, on the permanent magnet, the cylinder magnet, it will be slowing down. This one will be slows down, and then it will be in the slow it down because the Lenz's law says that it will be opposed. It will be opposed of changing. Okay, so this is what happened. It slows down, and then at x actually it will be a constant. It will not slowing down. It will be it will be as a normal, and then as s when it goes down back, it will be slows down. This is because you see that at n, at this area, okay, at this area, okay, there will be a different of flux. So when it entering the flux and is having a flux over here, when it enters a flux, a change of flux, there will be induced current. So there will be what you call a change of Lenz law. Means that the Lenz law will be occur at that point. But at this side, there will be no change of flux because the flux will be constant at this side. At this point, as when you going to out of the region where we have electric flux, it also will be experiencing a slows down, okay, a slowing down of a drop. So the answer for this question is when we have x. When they add the x, d flux over dt will be equal to 0. So there will no Lenz law happens at that point. So the answer will be at the x only. So what happened is, okay, when it drops down, okay, this is a metering. It will be slowing at this point, and at this point will be as a normal, and then at this point, when it drops down, this one will be slow also because a change of magnetic flux from we have a bigger magnetic flux to non-magnetic flux. Okay, zero magnetic flux. So question number 12, answer will be B. Goes to the question number 13. A flat circular coil 100 turns, each of area 0.06 meters square is placed with active parallel to uniform magnetic field. The flux density of field change from 50 millitesla to 10 millitesla over a period of. This is a very easy question. You just apply in the equation. So you know the equation E in use will be equals to N times A change of B divided by change of T. So you just substitute everything. You have 100 and 0.060 and times with 50 minus the change of B 10 in bracket times 10 power of negative 3, and you have down there you have 5 milliseconds. So you have answer induced current will be uh, 0.048 volt, or you have 48 millivolt. So answer will be C. This is very basic question, very direct. You just substitute the numbers. Okay. Then we go to question number. Any question about this? Question number 13. Okay, no.
No, sir.
Okay, question number 14. Alternating current is represented by equation I equals to 3 sin 20 omega t, where t is in second, where is the mean power developed by the current resistor at resistance 8 ohm. Okay, so I equals to 3 sin 20 pi t. Okay, so in the general equation, you know that I equals to I naught sine omega t. Okay, so mean power, you have to, if you want to have the mean power, you have to get uh, uh, P mean, you have to get P, no, sorry, I RMS square and times, sorry, it's a R, I square R. Okay, so in this case, if given you I naught, okay, I naught as in the equation, so you have to turn I naught into I RMS. So I RMS is actually I naught divided by square root of 2. Right. So I naught divided by square root of 2, where I naught is 3 divided by square root of 2. Uh, and then you put in inside in the equation. So P mean is equals to um, square root of 3 over square root of 2 squared and time with 8. There you have 36 watt. So answer will be A, 36 watt. Okay. Question number 15. This circuit below, where must capacitor must be connected to obtain smooth DC output. Okay. So this is a diode. You have seen the diode. It's not in our syllabus, but the diode here is a function of a filter. let's say this one goes, if the arrow shows to the right, so it will filter. Let's say we have a current like this, up, down, up, down, up, down. You see the current I. So when it goes from W, this is from W. When it goes to X, what happen is it actually filter out the negative. So what happened at X is up here only, this side. Okay, this is current that flows through a diode. Like that. So we need a capacitor to smoothen out this wave. Okay, to smooth out this wave, we need a capacitor that can charge above, charge and discharge like this, and then charge back and discharge, and charge and discharge. So eventually you have actually, if you have a good capacitor with a with a precise capacitance, and no, it's not precise capacitance, it's a precise time constant. Actually when you end up with a DC current like this, okay, a DC current, because of charge and discharge of the capacitor. So we need a capacitor in this diagram, and it cannot be, we have to make sure the capacitor should be parallel to no, capacitor should be parallel to the resistor, okay, in order it to work. So it should be like this, okay, the capacitor should be like this, like that, or we can say it's going to the Z, okay. So you see, if we have a if we have this kind of arrangement, actually the when it was positive side or negative side, a positive side, negative side, it can be filtered out by the capacitor, okay. So this one will be smoother out the 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 graph of the graph of the wave, okay. Okay, so answer will be, any question on this question number 15? Do you have any question? Anyone? Question on question number 15? You have
No,
question?
sir.
No, okay. So we go to question number 16, a structure. A conducting radius sphere of R is charged, and the surface of charge density of the surface sphere is sigma. Explain why the charge only the surface of the sphere. Uh, so what did you put, Usha, as answer? Usha, what did you put as answer in the as your in your paper? Usha?
I put the charge on the surface is only on the surface of the sphere because
Mm,
there is no potential difference.
no potential difference. It's not very accurate. Okay, you see, this is the whole thing. Let's say we have a sphere, a metal sphere is a hollow, or we can have a solid metal sphere. If you put a positive charge at the middle, what happen is all of them we experience a repulsion because they cannot be near. They experience repulsion. So the Q
Mm.
over here goes to the furthest they can go. Right? They want to be the furthest where they can go actually at the surface of the sphere. Okay? So they cannot go above more than the surface. Right? They cannot go more than the surface because they need more energy to excite them to be more on the space. There will be that actually what happens when we have a spark because the charge is uh, more than uh, more than what we have by the surface of the sphere. So what happen is the charge the charge inside inside, okay, will experience, okay, repulsive force, okay, force between them, okay, uh, until they reach the surface of the sphere. Okay, until they reach the surface of the sphere. Okay, that is the main idea, the main facts why there are no charge on the inside of the sphere, either it's hollow or it's a solid. Okay, so B1, right expression. Okay, symbol R, with the symbol R, sigma infinity of space for the electric field at the point P instant for the center of. Okay, so let's say we have we draw a graph, we saw a sphere here, and then this is origin. Okay, over here. So we have a point P. So let's say we have a here point P, point surface. Surface I put as what? R, and point S out of the sphere. Okay, at point P, you know that by the Gauss law, okay, or you can use the Gauss law to derive, but actually we have E equals to 0. Use Gauss law. Okay, Gauss law. Okay, E equals to 0. And at R, okay, because it's a sphere shape, R equals to at R, E equals to Q over 4 pi epsilon naught R. Okay, so this one will be the equation. But if since that we need to use sigma, and sigma is actually charge divided by the area. Okay, the area. So this area is a area of a sphere. So we can change this Q. We can substitute Q 4 pi and R. Sorry, this one has R square, and R over here as the area a of a of a sphere. So we can change that into sigma divided by epsilon naught. Okay, sigma divided by epsilon naught. So this one will be the answer at point R. At the point S, at the point S will be Q divided by E will be equals to Q divided by 4 pi epsilon naught and S squared, because it is not R already, it's S further than R. Okay, so we have to use sigma. We cannot use all the things sigma. So we time both with R squared times with R squared. So if we times R squared, we have R squared Q divided by 4 pi epsilon naught S squared R squared. Okay, and we use back the sigma. Now we can use a sigma because we have 4 pi epsilon naught R squared, and we have a Q. So we have epsilon naught sigma R squared divided by epsilon naught and S. Okay, so this one will be the answer for the whole thing. So the first one will be E equals to 0. You can use the Gauss law. You have learned Gauss law. He says that how many charge inside the inside the up inside the Gaussian surface, because there are no charge inside the Gaussian surface, so E will be equals to 0. Second one, we have R equals to sigma divided by epsilon naught. And third one, when the point of S, it will be sigma R squared divided by epsilon naught S. Okay, we have to times with R squared because we, in the equation you need to use a sigma. Okay, and the equation B1, B2 and B3. You keen? Okay. Yes. Yeah, Kihang. S squared. Oh yeah, yeah, it's S squared. I forgot. Yes, it's S squared. Thank you for reminding me. It's S squared. Okay. So, any more? Any question? Nope. Okay. So we proceed to question number 17. And AC voltage is 5 volts. 5 volts is step up to 20 volt using a transformer, so it's a stepped up transformer. The output is connected to a resistor of 12 ohm in a complete circuit. Okay, output complete circuit. The efficiency of transformer is 85%. Calculate the current in the secondary coil. So if I may draw, it has 5 volts, 5 volts, and then a step up at the first coil and second coil. Okay, 5 volt to 20 volts, and the output is connected to a resistor 12 ohm. Okay, the efficiency of the transformer is 85%, so this 100 it turns into 85%. Calculate the current in the secondary coil. So current in the secondary coil, we have V equals to IR, okay, Ohm's law, and I equals to V over R. So we have 20 divided by 12. So we have 1.67 ampere. Very easy. Question number B. Output power. Uh, P power equals to IV or VI. So equals to 20 times with 1.67. Is another way, or 1.67 times 20. Okay. So you have power will be 3.4 watt. Okay. So input power. Okay, input power we don't have the numbers. We only have the 5 watts. 5 volts. Okay. So we can use to relate by the efficiency. So for C, efficiency will be equals to P output divided by P input times with 100%. So P input, power input will be 333.4 divided by 85% times with 100. Okay, so we have 39.3 watt as a power input. Okay, so D, for D, current in primary coil. So I equals to P over V. Okay, P equals IV equals to 39.3 divided by 5. So we have 7.86 ampere. Okay, so that will be the answer. Actually, it's not very hard for question number 17. You are always using the back the P equals IV and V equals to IR. Okay, any question? Question number 17.
No problem.
No problem. Okay, now we goes to question number 18. Okay, define capacitance. Is in your MAS, right? Define capacitance. What is capacitance? It's a charge. It's a ratio of charge, okay, to the potential difference between two plates of capacitor. Okay, ratio between how much potential difference between the plates. So C equals to Q over V, right? So B, a capacitor of a capacitance 20 microfarad is fully charged from 80 volt DC supply. Okay, fully charged for okay 80 volt. Yeah, you have a V over here, and you have a what's called C, C and V. Calculate the charge stored by the capacitor. Okay, so we need to find out the charge in the Q, right? The charge is Q. So Q equals to CV. Okay, it will be equals to 20 times 10 power of negative 6 and times with 18, and you have 3.6 times 10 power negative 4 coulomb. Okay, question number 2, this is 1. Question number 2, calculate the energy delivered by 18 volt power supply. So E equals to QV. Okay, uh, so 3.6 times 10 power negative 4 times with 18. So you have 6.48 times 10 power negative 3 joule, unit of energy, joule. Remember, question number 3, calculate the energy stored by the capacitor is E equals to half CV squared or half QV, can be also used. Okay, so it's half Q, we have 3.6 times 10 power of negative 4 times 10 power negative 4, and V is 18 and equals to 3.24 times 10 power of negative 3 joule. Okay. Okay, explain the difference between answer B2 and B3. B2 we have 6.48 and B3 we have 3.24. Why? What happened? The different? Why we have a different of answer here? Okay, so it's because half of energy is lost as heat. Okay, as heat in the resistance. Okay, of the circuit. So this resistance, okay, uh, is the one making of the energy loss. Resistance in the circuit. So it is not actually a pure capacitor. It's not a pure capacitor where we have a pure capacitor does not have any resistance or self inductance. So the half of energy is because of the resistance of the capacitor. Okay, so we have 5 more minutes. Okay, 18C, the 20 microfarad capacitor in B. Okay, the same capacitor was charged from power supply to a resistor of resistance. So we include now we include resistor in the question 2.5 kilo ohm to calculate the time constant for this circuit. Okay, now we know that the time constant tau equals to CR, and it will be 20 times 10 power negative 6 times with R, that is 2500 ohm, and it will be 0.005 second. So time constant will 0.05. B number 2, when the capacitor is charged from zero charge, how long it takes a potential difference V across meter to reach a 99% of final value. So we have 0 goes up. Okay, so when 0 until 99. Okay, uh, how long, how much the time, needed, T, how much the time needed. Okay, so it was saying that 0 charge, 0 to reach. Okay, so V, I think I need to erase some of these uh, writings on the board. Okay, okay, goes back to pen. Okay, so we know that V equals to V naught, uh, and we have a, is it V naught? I minus a V naught, yes, correct. I minus E negative T over CR. Okay, this is a general equation for this is charging, right? This is charging. So V minus I minus E naught. So V divided by V naught, okay, it should be V over V naught, it should be 0.99%. Alright, because it says in 9.5% of its final value. So V over V naught is equal to 0.99%. So, and V over V naught is actually it's actually 1 minus E minus in power of negative T over CR. Okay, so, the whole thing is 0.99. Okay, so we have E negative power of negative T over CR equals to 0.01, right? Because 1 goes over the right side, we have 0.01. So T over CR is equal to ln negative ln or ln or negative ln 0.01. So T equals to negative ln 0.01 and times with 0.05, then the time will be 0.23 seconds. So it takes 0.23 seconds from 0 V, okay, initially 0 V, and it takes until 99% of V. Okay, any question? So tomorrow going to continue with question number 19 and 20. And one more thing, I'll release model paper 3. Okay, so tomorrow as we discuss question number 19 and 20, you can also do question you start with the paper 3 model paper. Okay, any question on today's lesson? Any question on today's lesson? No question. No question. Everyone? Usha, Kihang, Keshika? No. Okay. So going to stop the lesson today. So tomorrow at same time, 4 o'clock. Okay, we continue with question 19 and 20. Okay, thank you all. See you tomorrow.